Hello everyone, thanks for tuning in. My name is Arnold and this is Kisembo Academy. In today's session, we are basically going to be deriving some standard formula for projectile motion. This standard formula that we are going to derive for projectile motion is the formula for the maximum height a projectile can ever reach, the formula for the range of a projectile, that is the horizontal range, then the formula for the time of flight for projectile motion. We are going to derive those, and we are going to derive those while just playing around with these three common equations of motion. Now, after deriving this formula, it's going to be important that you have this formula at your fingertips. In some jurisdictions, some people are allowed to have separate booklets, formula booklets, while they're doing their exams. In some examining bodies, they are not allowed to do so, and so you're supposed to kind of cram. But before you cram them, it's important that you're able to understand where these formulas come from, how these formulas are derived. Whereas we are going to derive this formula for time of flight, for maximum height, and the horizontal range of a projectile motion, when it comes to numbers, it's not always going to be the case that you will have to use these formulas to solve questions. Sometimes you're going to have to apply these three equations of motion to reason out numbers and be able to calculate numbers without necessarily using the formulas we are going to derive in this session. So that is why it's important that you're able to understand how these standard formulas for time of flight, for maximum range and maximum height of a projectile use, it's important that you understand how they're derived, because the reasoning behind how they are derived is going to be the reasoning you're going to be using in trying to do some worked examples or in trying to do some numbers. We shall be doing some numbers in the upcoming session. So let's get into the video today and let's start deriving. So in the derivations we're going to do, we are just going to basically play around with these three equations of motion, and it's quite easy. So let's first get a diagrammatic representation of a projectile motion. Like we all know, when a projectile is in motion, let's say this is the ground level, ground zero. Let me call it ground zero. When a projectile is moving, it moves up like that, and then eventually it comes down there, like that. So as that motion is happening, this is the particle. It could be a ball or something. This point where it is beginning from is what we are calling the point of projection. Now, at that point of projection, a projectile is always takes off with an initial velocity, which we are always going to denote u. As it's taking off with that initial velocity along the road here, along its journey here, its velocity keeps changing direction. And the velocity that keeps changing direction here as it's moving along its journey here is what we're denoting as v, the final velocity. This, when it's beginning, it's the initial velocity u, so as it's moving along, that's the final velocity. We all know that the distance it covers, this horizontal distance that is going through the point of projection up to here, this is what we're calling the horizontal range, and this is the maximum height it achieves while it's moving. So there are certain characteristics that we need to know in relation to these three equations of motion that normally happen as this projectile is moving, this particle. One characteristic you need to know about this motion is that when it's reaching its maximum height, its velocity is zero. So if it reaches maximum height and its velocity is zero, because it has paused momentarily before it comes back down to this ground zero level, how can we use that information to try and derive a standard formula using this? If we use the third equation of motion here, which is this one, and we say that when the final velocity is zero, what becomes of this? How can we use this to end up with, an expression, a standard formula? So let's get started with that one. So when a projectile is at maximum height, its final velocity is zero. So let's get to the third equation of motion. V squared is equal to u squared plus 2as. So we shall go ahead and say that v squared is equal to u squared plus 2as. That is the third equation of motion, and we are saying that at maximum height, this value of v is equal to 0. So when this value of v becomes 0 at maximum height, in the context of that projectile motion, what becomes of the rest of this? So let's proceed. So this is going to be 0, is going to be equal to the initial velocity. Now take note that one thing you need to know is that here, when this thing is taking off from here, it is taking off upwards, right? To perpendicular to the ground. Like, okay, this initial velocity, it is going off at a certain angle to the horizontal as it's going up. So the convention here is that everything that is going up is positive. And of course, in this case, it means that if this velocity is moving upwards, it means that this is positive velocity. Remember, velocity is a vector quantity. So upwards is positive, and definitely if we ever get to deal with a projectile motion where this is moving downwards like that, it would mean that at that point the velocity is moving downwards, but we shall come to that in a later session. So when it's moving up, that is upwards, it's a positive velocity. It means also that even the displacement, this is like ground zero. So if the displacement is in that direction, it is positive displacement, and if the displacement is in the opposite direction, it means that is negative displacement. And when we are talking about displacement, we are talking about in reference to this ground zero, the ground where the point of projection is that platform. So since this is an upward motion, we are supposed to resolve this initial velocity in the vertical direction, because this is motion going upwards. So we resolve this in the vertical direction. And since this is going off at an angle theta, if I may extrapolate this triangle here like this and redraw it here roughly, this is our initial velocity, that's our angle theta, and we're supposed to resolve this velocity in the vertical direction, in this direction, where in this, which is that, you know, as it's moving up. So you'll find that this resolving this is going to end up, it's going to be u sine of theta. That is the component of the initial velocity in that direction. So meaning that right here, our initial velocity here, that's how it's going to be represented. We're going to say it is u squared sine squared theta, like that. Then that is going to be, now it's going to be plus 2 times a. What's the acceleration? Now remember, this is the ground. The acceleration due to gravity always acts downwards, but this particle is moving upwards. So if this particle is moving upwards, it means it is moving against gravity. Because it is moving against gravity, it means that our acceleration here due to gravity is going to be a negative value. It can't be a positive value. Why? Because the particle is moving against gravity. So it means it's going to be 2 times our acceleration due to gravity is negative g times s. Now remember, s is displacement, yeah? And remember here, still we said that displacement will be positive when you're moving upwards, it will be negative when you're moving downwards. When velocity is 0, or when the particle momentarily pauses when velocity is 0, we have attained maximum height. So in other words, the displacement here, the value of s, remember we're counting this value of s, the displacement from ground zero. So the displacement here, when the particle momentarily pauses, that is when the velocity is 0, that displacement s is actually the maximum height. So it means that in this case, this value of s becomes our capital H, like that. So after getting that expression, let's ease it up a bit. It means that here 0 is going to be u squared sine squared theta. This can become minus 2gh. So from this, we can actually go ahead and get our expression for maximum height. Our expression for maximum height by making h the subject of the formula. Let's take this thing let's get this thing here. Let's take it that way. So this becomes 2g capital H is going to be equal to u squared sine squared theta. When we divide both sides here by 2g, this is what we end up with. This goes with that. You remain with capital H as u squared sine squared theta. Divide that by 2g. Now this is the expression for maximum height of a projectile motion. The maximum height of a trajectory from the ground zero. So that is how we derive this. In one of our previous sessions, I was able to derive this same expression, but I used a different approach. This is just another way of approaching it. What I would like to bring to your attention here is the reasoning behind how we play around with these equations of motion to arrive at these expressions. So in this case, we use the third equation of motion and we are able to get to this. So let's get on to the next. Let's get back to our diagram. So one of the characteristics of this trajectory is that when it reaches at around here, it momentarily pauses, and when it momentarily pauses, its maximum velocity is 0. So we've used that characteristic of its maximum velocity being 0. We plugged it in here and we were able to come up with this kind of expression. Now somebody might ask me, why did we choose the third equation of motion? Why didn't we put in this, why didn't we use the first equation of motion? Okay, let's use also that in the first equation of motion. Let's plug in that characteristic and let's see where it takes us. So let's say this is V is equal to U plus AT. That's the first equation of motion. And now we are saying that using that, when we reach maximum height, the velocity is 0, right? So when at maximum height, velocity is 0, is going to be, that is u sine theta, that is that, and of course that's going to be plus gravity, which is negative g, times time. Now this time, definitely, because we said maximum velocity since we said that right here the velocity is 0, when it is about to turn back down, the velocity is momentarily 0. It means that since we said the velocity is equal to 0, it means that this value of t, the time, is going to correspond to when the velocity is the time taken to move from here to there. So in other words, this value of time t is representing the time taken to reach this condition. It is the time taken to reach maximum height. So it's going to be this times capital T, let's call it t prime, and let's say that this t prime is the time taken to reach maximum height, because it's at maximum height that the velocity is 0. So this is going to become the expression will end up being u times sine of theta minus g times t prime. Let's get this expression. Let's take it that way. So this is going to become g t prime is going to be equal to u times the sine of theta. When we divide both sides by g, we end up with our expression of t prime giving us u sine theta over g. And so this right here is the expression for this is time taken to reach maximum height. So I think you can see this is the time taken to reach the maximum height. And this was the maximum height reached. I am doing this recap because some people just really cram how to derive these expressions. And it's not good to cram. Just understand the reasoning behind how these expressions are arrived at, and you'll be able to arrive at them at any angle. So let's move on to the next expression. So on moving on to the next expression, it's going to take us back to our trajectory. Looking at our trajectory here still, this is our projectile. It's moving like that. We were able to actually get two expressions by just utilizing this characteristic that when the particle is up here, when the velocity is 0, we were able to get two expressions using that characteristic. We were able to get the expression for maximum height reached. We were also able to get the expression for the time taken to reach that maximum height, just playing around with these equations of motion by just using that characteristic. Now there's another characteristic here. Here it is at 0 displacement. The particle is at 0 displacement. It's going to move up, then it's going to come back down. So you realize that as it is moving, when it's moving in the upward direction, it is positive displacement. If it moves below this line downwards, in other words, if this particle is to go down like this, this would be negative displacement. This would be positive displacement, and here it would be negative displacement if it is going below this line. So we need to put that at the back of our mind. So in other words, when I kick a ball and it goes up, then it comes back down here, the displacement at this point is going to be 0, and the displacement at that point is also still going to be 0, as long as it is still in this horizontal range or in this horizontal plane. So how can we use that characteristic? Can we plug in that characteristic in these formulas? And when we do so, what expression shall we be getting? So let's proceed. So of course, as we proceed with that, we know that the expression here that is having displacement, we have this one, the second equation of motion. It is having displacement S. And here we are looking at the displacement in the y direction. So the displacement is ut and this. So let's do that. It's going to be S. Displacement, first of all, S is going to be equal to ut plus a half a t squared. So this displacement, let's say displacement in the y direction. Now we are looking at specific at this displacement in the y direction. What is so the displacement in the y direction is going to be equal to, so that is u times the sine of theta. That is the this in the y direction times the time as it's moving upwards and downwards times the time. That's going to be plus, that's going to be a half, multiply that by the acceleration due to gravity. Acceleration is negative since it is this particle is moving against gravity, times negative g times the time. That is times time. Now we need to take note also that this value of t we are looking at here, we are looking at displacement in the y direction. We are looking at displacement in the y direction, and this is the expression we have gotten. But now when when the displacement is 0, when this value is 0, it means that this particle is either at this point or at that point. If the displacement is 0 and this particle is at that point, it means that we will be having the value of t will be the time for the entire flight when it is at that point. So let's proceed. If the displacement is 0, that's the characteristic we are trying to maximize, or we are trying to exploit. When the displacement is 0, this means it's going to become u sine theta times t. So what times t, all right, then this is minus a half g t squared. Well, that is supposed to be squared. So again, from here we can get this, take it that way, this becomes a half g t squared is going to be equal to u sine theta t. One of these t's will cancel with one of those. We shall end up with when we make t the subject of the formula, it's going to become u sine theta times 2 over g. This is the same as saying 2 u sine of theta over g. From what you can see, this 2u sine theta g is going to be the time for the maximum time of flight. This is the expression for time of flight. That's the expression for time of flight. And if you're to compare this expression to the expression we got earlier for time to reach maximum height, if you look at this, this is time to reach maximum height and then the time of flight. You know this is u sine theta. You see this one also u sine theta. It means that time to reach maximum height, you multiply it by 2 and you're able to get the time of the flight. Why is that? Because the time taken to reach the maximum height is just half the distance. So it means the time to come here to there is just this expression. Then it means it's going to be the same time to move from that maximum height to the end of the journey, to the end of the trajectory. So it means that this time to reach maximum height, if you multiply it by 2, which is what we have attained here, if you multiply it by 2, this times 2 is going to give us the time of the flight. I think you're able to see the relationship between the two. We're able to get this expression by just utilizing that piece of information, that characteristic, that at 0 displacement, the vertical at the starting point, that the vertical displacement is always 0, and we're able to plug that in here, and we're able to get that expression for time of the flight. Now, now let's take note of this, that when you look at this expression in a way, the way it has been interpreted here, the calculations, this is more like a quadratic equation. If you were to look at it, it has some characteristics of a quadratic equation, and if you're to interpret this as a quadratic equation, you'd end up with 2 values of t. The first value of t will represent the time when the particle was at this point, and the other value of t will represent the time when the particle had reached this point. In other words, if we were dealing with real figures and you plug in here the values of, the values of theta and the values of u here, the way it is, you should be able to get 2 values of t, because this is more like quadratic in nature. And when you get those 2 values of t, the first value of t is the time when it is here, because that is when it is at 0 displacement. The second value of t will be the time of flight. That is when the particle is here, when it has completed the journey, the trajectory. That is something to be explored in the calculations in the upcoming sessions. And now finally, we would like to look at the range, the horizontal range of this. When this ball is kicked, it goes out up to there. What distance does it cover down here like that? Now, remember before we were considering this motion in the vertical sense, yeah? But now here we are looking at distance moved from this point to that point, and that is more like distance in the horizontal direction. So how do we find that? We can find that using the simple formula of distance is equal to speed times time. So I'll simply come and say that the distance covered from here to there, the horizontal distance, is given by the speed, multiply that by the time taken. So we shall ask ourselves, the distance moved here to there, it's what we are looking for, it's what we are calling range, let's call it capital R, is going to be equal to the speed. Now the speed with which this thing is moving from here to here, remember, it means that this velocity here, this time we are supposed to resolve it along the horizontal. Now resolving of forces is just the most previous session that we have been handling. So resolving this velocity along this direction is going to be u cos theta. we have resolved this velocity along that so that will act as the speed times the time. Now what's the time? What's the time taken for this distance to be covered when this particle is moving up and then it comes back down here? What time does it go? Is it going to be taken? Definitely the time taken to cover this range is the same as the time taken by this particle when it is in air. In other words, it's the time of flight. By the time this horizontal distance is covered by this particle that is moving up, the time taken for it to be able to cover this is the time of the flight. So it means the time here we are going to use is the time of flight, and we derived the time of flight here. The time of flight is right there, you know. So this is going to be times this time of flight, which is going to be 2u times the sine of theta divided by g, and the rest is just arithmetic. This times that, you're going to mind it's going to become u times u is u squared, then times 2 cos theta sine theta, divide all that by g, and that's going to be equal to u squared. Now u squared using trigonometry, actually this is more like you could even, this is, we've gotten the final answer, we're just trying to refine it. If you look at this is a trigonometrical identity that could mean sine to theta. Now this is trigonometry, it's another topic in pure mathematics. I am assuming that you have learnt about this, or you should be having prior knowledge about trigonometrical identities, that 2 cos theta sine theta is the same as sine 2 theta. So it means that this can be simplified further into u squared sine 2 theta, divide that by g, and this is the expression for our maximum range. So we've got the expression for range, and the range here we're talking about is basically the horizontal range, this distance here from here to there. But when I was trying to derive this expression for range, we used distance is equal to speed times time to arrive at it. Now somebody might ask me and is like, but I thought for us to derive all these expressions we are only going to play around with these. Why is it that in this specific this specific derivation you started with distance is equal to speed times time? Where is this coming from? Let me answer that. This distance is equal to speed times time, this expression is actually coming from one of these expressions. Specifically, it's coming from the expression or from the equation for displacement. Now take note, previously when we were looking at this diagram here, right here as you see, I explained the issue of displacement in the positive direction and in the negative direction, and that's the kind of displacement we were talking about when we are dealing with, displacement in the y. That's why I said this, I put this as s subscript y, as in displacement in the y direction, and then we went ahead and did this. Now when we are looking at the distance here, the range, the distance covered in the x direction, actually it is the same way as saying it is displacement in the x direction. So if we still used this same expression and we said now we are looking for the expression, the distance in the x direction, you will see how we arrive at this expression of distance is equal to speed times time. So let me explain it further. This is how it goes. So we know that s, this expression, is equal to ut plus a half at squared. But now this range, this distance is actually, if this is displacement in the y direction, then this is displacement in the x direction, this one. So it means this is displacement in the x direction is given by ut plus a half at squared. So let's go on with the substitutions. Displacement in the x direction, which so happens to be sx, is going to be given by u Now looking at our u here, remember here we are supposed to resolve this u in the x direction. So if this is u sine theta, so in this direction this is u cos theta. We are to resolve this initial velocity in the x direction, and so this is going to become our u times the cosine of theta. Multiply that by the time taken to cover this range, this distance, that is times t. And remember, the time taken to cover this is the same to cover the x distance, or to cover the displacement in the horizontal direction, is the same amount of time taken when the thing moved up and came down. We found that value of time in our earlier expressions. This is the time taken for the whole flight, time of flight, which is t2u that. So it is the expression, the value of t here. So that is going to be equal to, it's the same as this. Well, let me substitute this value of t direct here by putting that expression there. So this is going to become 2u sine theta over g, like that. So plus, remember we are following this, plus that is going to be a half times a times t. Now remember, here we are looking at horizontal displacement. And in the horizontal displacement, the truth of the matter is that in the horizontal displacement there is no gravity. Gravity only acts in the vertical displacement. In the horizontal displacement there is no gravity, so it means this value of acceleration is 0. Now if that value of acceleration is 0, it means that this whole term is going to die, and so this whole term is 0. So that if this whole term is 0, it means that as far as the displacement in the x direction is concerned, or call it the horizontal displacement, we only have the velocity times the time. And so that's how you end up with our displacement in the x direction is going to be equal to, this is 2 times u cos theta squared sine 2 theta over g. So from this you're able to see that because now this thing is 0, you realize that what we are remaining with is displacement is equal to velocity times time. You realize that this expression is the same as saying displacement here, the displacement here we called, you realize that here the displacement here is the distance here. The velocity here is the speed, and then the time. In other words, this is an expression. This expression is in vector form. In other words, this is displacement, distance. Displacement is a vector quantity. Distance is a scalar quantity. Velocity is a vector quantity. Speed is a scalar quantity. Whereas they are having the same units, one is a vector quantity, the other is a scalar quantity. So this is just an alternative approach. Okay, this is explaining why I simply went ahead and said distance is equal to speed times time and ended up with this expression. You see that we are ending up with the same expression, but actually where it is coming from is that it is all coming from this expression for displacement. Here is the displacement in the x direction, and then there is the displacement in the y direction. In our upcoming sessions, as we will be, making these various calculations, we are going to be playing around with this expression a lot. And in this expression, we shall be, showing displacement in the x direction, displacement in the y direction, coming up with the formulas, and then, trying to find the missing links and the unknowns. So in this session, we've been able to derive some standard formula for projectile motion. We've been able to derive the expression for the horizontal range, the maximum horizontal range. We've been able to derive the expression for maximum height that a trajectory can reach, then the time taken to reach that maximum height, plus the time taken for the entire flight. As I've been trying to derive this formula, you've been able to see how I was able to arrive at this formula. But more importantly, I I would like you to see how we were able to derive this formula. Not all questions that we are going to do about projectile motion are going to require us to use these formulas that we have derived. Sometimes the formulas may not apply, and you will need to reason out a number using the approach that we have used in this video. I'll give an example. For example, here we're able to use the reasoning behind that the displacement, the vertical displacement is 0 at the beginning of the flight and at the end of the flight. But sometimes the displacement might not be 0. It might be another figure. So you should be able to know how to use this equation of motion to be able to get your answer depending on the question. So in our upcoming sessions, we are going to start doing some worked examples on the projectile motion, and some numbers might require us to use these formulas that we have derived. Some numbers might require us to reason them out from first principles. So I'll catch you in the upcoming sessions. Like this video if you like it. Don't forget to subscribe. Check out other sessions on this channel. Remember to share this video with your friends. My name is Arnold Rangakuramia, and this is Kisembo Academy. Take care.